Okay, last meeting, we have this section, chapter 3, section 3 of chapter 5, sampling from the normal distribution. First, we consider the properties of the sample mean and the sample variance. According to theorem 5.3.1, given that we have a random sample, x sub 1 up to x sub n from a normal distribution with mean mu and variance sigma square, we have proved that the sample variance x bar and then the sample mean x bar and then the sample variance s square are independent random variables. And then we have also uh, we also proved that x bar has a normal distribution with mean mu and then the variance is sigma square over n. We are left to prove the property letter C, in which the product of n minus 1 and s squared divided by sigma square has a chi-square distribution with n minus 1. Yeah. Prove letter C of theorem 5.3.1. Let us recall first that uh, the chi-square distribution, no, is a special case of a gamma PDF. Okay, let us try to recall first the gamma PDF. Supposing x here is a random variable having a gamma PDF with parameter alpha beta. The PDF for this, we have 1 over gamma of alpha, beta of alpha, then we have x minus x to raise to the alpha minus 1, and then we have e to the negative x over beta, in which the support for our random variable x here, x greater than or equal to 0, but it is finite. Okay, in this case, if we choose y here having a chi-square distribution with p degrees of freedom, this is the same. No? As we have said that the chi-squared PDF is a special case of a gamma PDF. So this is equal to the gamma distribution with parameter, or we have this for our location parameter, we have p over 2 and then 2. Hence, the PDF for a chi-squared distribution now we have here 1 over, so we just replace alpha here, the alpha here by p over 2, and we replace beta here by 2. So this is now the PDF, no, the PDF for our chi-squared distribution. So where p is called the degrees of freedom, and then we have some facts regarding the chi-squared random variable. Okay, we use this notation now. Take note of this notation. The chi-squared random variable with p degrees of freedom. If z is a standard normal random variable, then the square of z has a chi-square distribution with 1 degree of freedom. Okay, we have proved this in chapter 2. It's actually in example 2.1.7. And then for letter B, if x sub 1 up to x sub n are independent, and then the x sub I has a chi-square distribution with p sub I degrees of freedom, then the sum, okay, this a finite sum of random variables x sub 1 up to x sub n will have a chi-square distribution, and its degrees of freedom will be the sum p sub 1 up to p sub n. This result, letter B, was also been discussed in example, no? In example in chapter 4. That's actually an application of theorem 4.6.7. So that's in example 4.6.8. So in application of the theorem 4.6.7, in which we have used the moment generating function of a gamma. Okay, so we have these facts about the chi-squared random variable. So let us proceed now in proving uh, property C of theorem 5.3.1, in which the product of n minus 1 times the sample variance S sub n squared divided by the population variance sigma square has a chi-square distribution with n minus 1 degrees of freedom. So to prove this, we use the principle of mathematical induction, and we use this notation x sub k bar. Okay, we have x sub k bar and then s sub k squared to denote the sample mean and variance, no, the sample variance based on the k observations. We have a note there that the actual ordering of the observations is immaterial. So just to facilitate the proof, we consider uh, the no the the observations to be ordered. Okay, so it says here that it is straightforward to establish that we have this equality in 5.3.1. It's easy to show that this equality is true. This is actually an exercise 5.15, and I'm going to give this also as another problem in your problem set number 3. Okay, so madali lang masyado ito. Algebraic, lang, yung gamit lang kayo ng your your knowledge in calculus as well as in algebra. Okay, so since we're going to apply the principle of mathematical induction, we consider n here, the smallest value for n, to be equal to 2. So if n is equal to 2, then we have here 2 minus 1. The answer for that is equal to 1. So we have s sub 2 square. Ang maiiwan dyan sa left-hand side, we have now s sub 2 square. While on the right-hand side of equation 5.3.1, so when n is equal to 2, in this case, 2 minus 2, so we have here 0. Okay, that is 0. Oh, no. Okay, we have 2 minus 2, so this is a 0. So the first term on the right-hand side of 5.3.1 will be 0. Itong part na to, that will be 0. So ang maiiwan na lang yung second term. So we have 2 minus 1, 2 minus 1 over 2. So we have 1 half. This is the 1 half. And then we have x sub n minus x sub 2 minus 1 bar. So we have here x sub 1. We have only x sub 1. It should be x sub 1 bar. But we know that x sub 1 bar will just be equal to x sub 1. Okay, so we have that s sub 2 square. And then since the distribution of this expression, x sub 2 minus x sub 1 over square root of 2 has a standard normal distribution. By the way, for this, if you have time, you try to verify this. This is very easy to verify. Given we have two standard normal random variable, x sub 1 and x sub 2, then this random variable x sub 2 minus x sub 1 divided by square root of 2 has a normal, standard normal distribution. You just apply what we have learned in chapter 4. Chapter 4. We have the original, we have the original random variables, say x sub 1 and then x sub 2. And then we have the transformation of these random variables, one of which we have x sub 2 minus x sub 1 divided by square root of 2. Okay, so it's easy to verify that this has a standard normal distribution. Okay, so if this is standard normal, based on our lemma that I've stated a while ago, the square of this standard normal will have a chi-square distribution. So this is true. Okay, so we have verified the first part of the principle of mathematical induction. So next part of PMI, we're going to assume that our statement is true when n is equal to k. Okay, when n is equal to k. So that means that k, okay, yung implication that k minus 1 times s sub k square has a chi-square distribution with k minus 1 degrees of freedom. And we're going to show that our statement again will be true when n is equal to k plus 1. So when k is equal to k plus 1, using equation 5.3.1, so we have n is equal to k plus 1. So in this case, no, itong part na to, n is equal to k plus 1. So k plus 1 minus 1, then we have here k. And then s sub k plus 1 quantity square. And then on the second term, on the first term of this, on the left right-hand side of 5.3.1, so we have k plus 1 minus 2, so we have here k minus 1. Then we have s sub k square. And then on the second term, we have here. By assumption, this is, or this expression has a chi-square distribution with k minus 1 degrees of freedom. So chi-square distribution with k minus 1 degrees of freedom. And then this one, we're going to show that the second term has also a chi-square, no? Has also a chi-square distribution with 1 degree of freedom. Chi-square with 1 degree of freedom. And then, we can now we can also show that these two terms having a chi-square distribution to be independent. And after that, we're going to apply what we have learned in the previous lemma, in which we have the sum of a chi-square, the sum of the chi-square distribution, in which these random variables having or these random variables are mutually independent, will have a chi-square distribution in which the degrees of freedom, is being added. Okay, so we have here yan yung sinabi dito. K has having a chi-square distribution with k minus 1 degrees of freedom. Here, a chi-square distribution with 1 degree of freedom. And at the same time, the expression k over k plus 1 times the square of x sub k plus 1 minus the sample mean x sub k bar quantity square is independent of the sample variance s sub k square. So first, let us try to check the independence between these two expressions. Say the independence of x sub k plus 1 minus x sub k bar square, and then s sub k, the independence of this, it follows actually from theorem 4.6.12. We know that x sub k bar and s sub k, the sample mean x sub k bar and the sample variance s sub k square, these two are independent based on the previous theorem. Now we have proved that one. And then the expression, this expression s sub k. Ano yung x sub k natin? The s sub k quantity square. Now, if we're going to use the equation 5.3.1 above, we have this result: 1 over k minus 1 times, we have here k minus 2. Then we have s sub k minus 1 quantity square plus k minus 1 over k. Then we have x sub k minus x sub k plus, s sub k minus 1 quantity square. So this s sub k square, it does not depend on x sub k plus 1. So if the sample mean x sub k bar and then s sub k square, they are independent. We have proved that the sample mean and the sample variance are independent. And then we have a functions. Okay, this time a function. We know also that this uh, s sub k plus 1 and then s sub k quantity square, s sub k square. These two are also independent since s sub k square does not depend on x sub k minus 1. Then a function, okay, a function of this s x sub k plus 1 and then, or we have this vector, no, a function of this vector would be independent of s sub k square. So, ano yung function? A function of this vector. So is the function of the vector. So these two now, ito siyang expression na to, and then this, another expression, these two are independent. Yung kulang na lang is to be able to show that this expression, the second expression on equation 5.3.2 has a chi-square distribution with 1 degree of freedom. So it says there, furthermore, x sub k plus 1 minus x sub k bar is normal, a random variable with mean 0 and the variance we have here. So implication yan, x sub k plus 1 minus x sub k bar. Copy to this. Will have a normal distribution with mean 0 and the variance is k plus 1 over k. So if you're going to, if we can show this, that this is true, therefore, k, we call this now as the scaled, no? As the scaled, as the scaled PDF. The scaled PDF. So we have k over k plus 1 times x sub k plus 1 minus x sub k bar, quantity square. We'll have a chi-square distribution with 1 degree of freedom. So, kung ma-show na natin ito na totoo ito, and then using the previous lemma, in which they are mutually independent, no? These two are mutually independent, having a chi-square distribution, then the sum will have also a chi-square distribution, in which the degrees of freedom will be added. That's why we have established the third property in theorem 5.3.1. Any questions or clarifications? By the way, guys, for this particular, no, for this particular expression, if you're going to show that one, you can also apply, no, the principle of mathematical induction, in which one part of the principle of mathematical induction, we have this. Ito. Actually, ang result nito, the result for this, we have x, parang x sub, sorry, x sub 2, oop, x sub 2 minus x sub 1. Okay, we have that, no? We'll have a normal distribution with mean 0 and variance will be equal to 2. And this would further imply, now that would further imply that x sub 2 minus x sub 1 over square root of 2 will have a normal distribution. Ayan, yan. Say for example, kung ang k value natin is 2, so kung ang k value is 1, so we have here 2 plus 1. Yung k plus 1 natin dyan, k plus 1 over k will just be equal to 2. So ito may iwan dito, x, k is 1, so x2 minus x1 bar. Itong part na to. So we have a normal distribution with mean 0 and variance 2. Yan yun, nasa itaas, no? Yan yun nasa itaas. So if you want to prove this, no, if you want to prove this a fact, you can apply the principle of mathematical induction for that. Okay, so we're done with improving the third property of theorem 5.3.1. We have here an additional remark regarding the independence of the sample mean and the sample variance. It can be established in a different manner using this lemma 5.3.3. We let x sub j has a normal distribution with mean mu sub j and variance sigma sub j squared, j from 1 up to n. And these are independent random variables. So the constants a sub ij and b sub rj, j from 1 up to n, I from 1 up to k, r from 1 up to m, where k plus m is less than or equal to n. Then we define these random variables, u sub I. So we have, excuse me for a while. Okay, so we have here u sub I. We have the finite summation. Tawag yan, parang may tayong may linear functions, no, of our random variables x sub j. And then v sub r is also a finite summation of v sub rj x sub j. We have also a linear function of our random variables. Then according to this lemma, the random variables u sub I and v sub r are independent if and only if the covariance of u sub I, v sub r is equal to 0. And then furthermore, the covariance of u sub I, v sub r will be just equal to this finite summation. Okay, so for letter B, we have a random vector now of random variables u sub 1 up to u sub k, v sub 1 up to v sub m. These are independent if and only if the u sub I is independent of v sub r for all pairs. So we have a pairwise independence of random variables, u sub I and then v sub r. I from 1 up to k, r from 1 up to m. So according to this lemma, we can check independence for random variables by checking the covariance term. That's actually on letter A problem, no? Letter A results. And then for letter B, if we're going to check the overall independence of the random vectors, we just check the pairwise independence of these random variables in our random vectors. Okay, so I don't intend to prove this lemma 5.3.3. Yun lang yung kanyang remarks regarding this lemma 5.3.3. So, itong section 3.2 of chapter 5, gusto ko sana ibigay ito na reading assignment, pero i-discuss ko nila itong section na to. So we have the student T and then the study course F. Okay, says here, the distributions derived in section 5.3.1, in a sense, the first step in a statistical analysis that assumes normality. So in particular, the most practical cases, the variance, sigma square is unknown. So thus, to get any idea of the variability of the sample mean as an estimate of the population mean, so it is necessary to estimate this variance, sigma square. So this topic was first addressed by W.S. Gosset, who published under the pseudonym of student in the early 1990s, 1900s. So the landmark work of student resulted in the student T distribution, or simply the T distribution. So if we have a random sample, x sub 1 up to x sub n from a normal distribution with mean mu and variance sigma square, we know that the quantity, this is x bar minus mu over sigma over square root of n. We'll have a normal distribution, standard normal distribution. Okay, so this is easy to show. We have this transformation. Take note. We can have z to be equal to x bar minus mu over sigma. Oh no. Saan na siya naitabuan eh? Excuse me for a while ha. Doc, have you seen my gloves here na?
No.
Gamit sa gloves. Okay, so over squared. Oh no. So if we're going to use the small z here, then we have x minus mu over sigma over square root of n. And then this would imply, if and only if we have x, we have sigma over square root of n, we have z, and then plus b. Hence, if we're going to determine the distribution of z, okay, based on the distribution of our sample mean, and then we have here the transformation, we have sigma over square root of n, z plus mu, and then we have here the Jacobian of our transformation here. So pwede na lang we have here sigma over square root of n. So if we take the derivative of this, partial derivative of this with respect to z, we have sigma over square root of n. And then we know that we have a one-to-one transformation from script A onto script B. Okay, then we can now show that the distribution of z has a standard normal distribution. Okay, so now for this particular expression, our sigma is known. If sigma is unknown, we can look for the distribution of this random variable, x bar minus mu over s over square root of n. So this would be a quantity that could be used as a basis for inference about our population mean mu when our population standard deviation was unknown. So to be able to determine the distribution of this random variable, we can re-express this random variable here by simply multiplying sigma over sigma, or multiplying by 1. So the equality remains or retains. And then we have this following expression. Ito yung maiiwan expression natin. So the numerator, we have proved this. It's already, it has a standard normal distribution. And then while the denominator will have a scaled, will have a scaled distribution. So from here, we know this fact already, that it has a chi-square distribution with n minus 1 degrees of freedom. Therefore, the square root of s square over sigma square will have this distribution. The square root of a chi-square distribution with n minus 1 degrees of freedom over n minus 1. And these two, again, these two random variables, this one and then this one, are independent. Because the numerator is a function of our sample mean, our denominator is also a function of our sample variance, and we know already that the sample mean and the sample variance are independent. So function of this independent random variables are also independent. Okay, so true yan siya, totoo yan siya. So for us to be able to determine the distribution of x bar minus mu over s minus sigma square, it is similar to finding the distribution of u over the square root of v minus p. So yung u natin is a standard normal, and then yung v, a random variable having a chi-square distribution with p degrees of freedom. And then we know that u and v now we are already independent. So we have this definition given a random sample from a normal distribution with mean mu and variance sigma square. The quantity, this quantity has a student t distribution with n minus 1 degrees of freedom. And then we're going to use the variable t with p degrees of freedom. Okay, we write this, random variable t having a t degrees of freedom, t distribution with p degrees of freedom. So this t equal to this expression, and the corresponding PDF of our random variable t will be here. Okay, it says here the derivation of the t PDF is straightforward. So if we start with u and v defined above, we have now the joint PDF of u and v. So before that, we're going to find first the joint PDF of the original, the original random variable. Actually, that's the original random variable rather. We have here the u and v. So this is equal to the product of the marginal. Okay, since u and v are independent. Okay, this is for the standard normal, and then this is for the chi-square distribution. So we have this transformation here, t. We have u over the square root of v over p. And then our w will be just equal to small v. So if we're going to determine our script A here, based on the original random variables, it should be the set of all ordered pairs uv such that the yung joint natin would be positive. And then if we're going to determine the script B here, it is the set of all t, small t and then W, this ordered pair, such that our P will be equal to U over the square root of V over P, and then our W will be equal to V. This is for some, okay, UV element of script A. Okay, based on our transformation, dito, based on our transformation, yung T, this would imply, no, for every ordered pair, TW, there exists only one uh, ordered pair U and V, such that T is equal to U over square root of V over P, and then W is equal to V. So this would imply that there exists a one-to-one, no? A one-to-one transformation, transformation from script A onto script P. So kung meron ganun, we can now, this would imply, no, that we have U here to be equal to T times the square root of W over P. And then our V would be equal to W. Then if we're going to take the partial derivative of U here with respect to T, we have the square root of W over P. The partial derivative of U with respect to W, okay? With respect to W, we have here, pwede naman yan, no? Square root of P, and then we have here 1/2 square root of W. Then the partial derivative of V with respect to T, that would be 0. Partial derivative of V with respect to W will be equal to 1. Okay, so this would imply that the Jacobian of our transformation here, which is the determinant of the matrix of partial derivatives, the square root of W over P here, T over square root of P, 1 square root of W, we have 0, then we have 1. So the answer for this is we have the square root of W over P. Okay, so from here now, ito yung Jacobian, no? The Jacobian of our transformation, the square root of W over P. Ayan. So if we're going to take the marginal PDF of T, ito ngayon ang hinahanap natin, the marginal PDF of T, supposedly we have this, okay? We have the proper integral of the joint, no, of U and V, and then evaluated on this points, and then times the absolute value of J, W. Okay, so W from 0 to positive infinity, T from negative infinity to positive infinity. Since we are integrating with respect to W, so we have from 0 to positive infinity, we change our limits of integration from 0 to positive infinity. And then we apply, no? We apply the joint distribution of U and V. So yan, ang result. Regarding for our the powers of W here, itong W natin dito, so yung part na yan. Ito ang part na to. So, yung exponents nila, P over 2 minus 1. And then itong W na to. So, na meron tayong plus 1/2. Plus 1/2. So, that would result to P plus 1 over 2 minus 1. Okay? So, ito na ngayon yung power niya. P over 2 minus 1. Ito part niya. That's for W. Itong P to the 1/2. Ito na yung P to the 1/2. And then sa T naman, itong sa E, exponential, we have here the exponential. Okay, simplifying, we have this result. Ito yung ating explanation for that. Okay, so notice that the integrand of this integral is actually the kernel of gamma p plus 1 over 2 and then 2 over 1 plus t square over p. So meron ng ito siya plus na siya plus 1 plus t square yan siya. Okay, 1 plus t square gamma. Diba? Notice? Recall. Lagyan na lang natin ito. Paano nga natin malaman yan? Kung yung x nga, merong gamma, alpha, beta. Ano nga kanyang PDF? 1 over, see we have here, gamma of alpha, beta of alpha, x raised to alpha minus 1, e raised to the negative x over beta. Okay, so ito na ngayon, W. Ito nga yung x dito, ito na yung W. W raised to. So yung p plus 1 minus 1. So, p plus 1 over 2. Yan na yan. While yung e to the negative x over beta, so yung beta natin ngayon will be just this. Kung titingnan nyo dito sa expression ng e natin dyan, no? E natin. Kasi ito yung, so w, itong w dyan, parang itong x na to. So, ito may iwan. That's our scale parameter. Okay, so ano yung i-multiply natin? We have the gamma of alpha and then beta of alpha. So gamma of, ito na ngayon, the gamma of, ito kasi yung i-multiply natin. No? So that we have the PDF will be equal to 1. So gamma of alpha, beta of alpha. So we have this. Okay, so this is now the distribution of our random variable t. So, yung t natin sa itaas, no, yung t natin sa itaas, itong t na to, will have this distribution now. Yan yung ating t distribution. Okay, so that's the derivation. Okay, another one, we're going to derive. Hindi ko na natin i-derive itong distribution ng Snedy course F. So we have a random sample, x sub 1 up to x sub n, from a normal distribution with mean mu sub x and variance sigma sub x squared. Then we have another random sample from a different population, y sub 1 up to y sub m, with normal distribution with mean mu sub y and then variance sigma sub y squared population. Take note that these two random samples are independent. So if you are interested in comparing the variability of these two populations, so one quantity of interest would be the ratio of their population variances. And this, we can be able to determine the information of the ratio of these two population variances using the ratio of their sample variances. So the sample, the F distribution allows us to compare these quantities by giving us the distribution of this. Okay, so we have the ratio of the sample variances and the population variances. So we can re-express this in this manner. And then we have now the ratios of these two expressions. and they are no scaled chi-squared variates, and they are independent. Okay, using these facts, no, alam natin ito that the product n minus 1 times s squared divided by sigma squared has a chi-square distribution with n minus 1 degrees of freedom. So s squared, no, the sample variance over the population variance, will have a 1 over n minus 1 times the chi-square distribution with n minus 1 degrees of freedom. So let's have this definition now. We have the random sample x sub 1 up to x sub n from a normal distribution with mean mu sub x and variance sigma sub x squared. We have also another random sample y sub 1 up to y sub m from a normal distribution with mean mu sub y and sigma sub y square population, in which these two populations or these two random samples are independent. We have this random variable denoted by capital letter F, which is the ratio, the ratio of these two expressions, s sub x squared over the population variance sigma sub x squared, and then the denominator s sub y squared over uh, sigma sub y squared. So this F now has a Snellius's F distribution with n minus 1, m minus 1 degrees of freedom. And then the probability density function is being defined in equation 5.3.9. We have that. So this big F here, as our random variable, has an F distribution uh, with P and Q degrees of freedom. So yan yung ating PDF. So yung derivation nito is almost similar to the process that we have used in deriving the T distribution. Okay, that's actually an exercise in 5.17. You have your original, no? You have your original random variable, U and V, U and V. U having a chi-square distribution with P degrees of freedom, V having a chi-square degrees of freedom, the chi-square distribution with Q degrees of freedom. And then you have now this transformation F. Yung new random variable natin will be in terms of F. And you can use another random variable, say W, for a function, no? A function of our original random variables. Then you can verify that the distribution of our F random variable is being defined in 5.3.9. Okay, so let's proceed now to example 5.3.7, an application of the F distribution. So it can be used for inference about the true ratio of the population variances. So consider the following. We have shown already, no? This quantity has an F distribution with n minus 1, m minus 1 degrees of freedom. So we can now calculate, if we have this distribution, we can now calculate the mean of this random variable. Supposedly, ito distribution ito, no? Distribution, pwede lang siya the expectation of this random variable f. F having an f n minus 1, m minus 1 degrees of freedom. Okay, so that's by definition. First equality holds, that's by definition. And then second equality by independence of this 2 chi-square distribution. And then the third equality, we know that the chi-square distribution with n minus 1 degrees of freedom, its mean will just be equal to its degrees of freedom. Kaya ito yung answer, n minus 1. But in evaluating the second expectation, m minus 1 over a chi-square distribution, we have to verify first that the expectation of 1 over W, kunwari, evaluate natin, kung naka-red dito, evaluate the expectation of 1 over W, where W has a chi-square distribution with p degrees of freedom. And then we can show that the mean of that is equal to 1 over p minus 2. So if we take p to be equal to m minus 1, itong part na to, m minus 1, then the expectation of 1 over W will be equal to 1 over m minus 3. Kaya ito yon, 1 over m minus 3. Itong numerator natin, napaiwan pa rin siya. So times 1 over m minus 3. Therefore, the mean for this random variable f will be equal to m minus 1 over m minus 3. Okay, so to verify, sulat lang natin ito. Say 1 over W. Okay, so definition from negative infinity to positive infinity, 1 over small w. And after that, the PDF of our W. W has a chi-square distribution with p degrees of freedom. So 1 over gamma of p over 2. We have 2 raised to p over 2. And then times W raised to p p over 2 minus 1, then e to the W, negative W, over 2. Okay, dW. And then W here. Ganun na yan. Okay, since we're integrating with respect to W, so magiging 0 to positive infinity na lang siya. Okay, we have here 1 over gamma p over 2, 2 to the p over 2 times. So yung maiwan dyan, meron tayong W. Meron W dito, may W dyan. So we have W p minus 2 minus 1 minus 1. And then we have e to the negative W over 2, dW. Okay, so from 0 to positive infinity, we have 1 over. So pwede natin ma-express ito as p over 2 minus 1 with the gamma of p over 2 minus 1 times 2 raised to p over 2 minus 1. And then we have W p over 2 minus 1 minus 1. Then we have e to the negative W over 2 dW. Okay, so itong part na to, we apply the gamma function. The gamma function, we know that gamma of, say, t plus 1 will be just equal to t factorial, no? T factorial. Okay, so applying that function, no? That gamma function, and we have that results. And then the second part will just be ito, 2p over 2. Pareho lang naman ito. Itong part na to, tsaka ito, pareho lang. So this would be equal to 1 over 2 times p over 2 minus 1. And then we have here 0 to 1 over gamma p over 2 minus 1. And then we have here 2 to the p minus 1. So we have w p over 2 minus 1 minus 1 e to the negative over 2, then dw. And this would sum to 1. Okay, so that would be equal to 1 over p minus 2. Ito, verified. So if we choose p here to be equal to m minus 1, then we have 1 over m minus 3. Okay, so that's the mean now of our f random variable having an f distribution. Okay, so by removing expectations, we have reasonably for large n, that would be approximately equal to 1. Okay, so to end this particular section, we have other properties of our f distribution. Been stated in theorem 5.3.8 that if if x has an f distribution with p and q degrees of freedom, then 1 over x will also have an f distribution but with q and p degrees of freedom. So that is the reciprocal of an f random variable is again an f random variable. Then second property, we have if x has a p distribution with q degrees of freedom, then the square of x will have an f distribution with 1 and q degrees of freedom. And then the third one, if x has a f distribution with p and q degrees of freedom, then this expression now, p over q times x divided by 1 minus the quantity p over qx will have a beta distribution with p over 2 and then q over 2 parameters. Okay, so any questions or clarifications? You don't need to uh, give you the proof of this theorem 5.3.8. You can try to uh, prove this theorem. Yes, LJ, that's correct. The chi-square distribution is a special case of a gamma distribution. If you have a gamma distribution with parameters alpha, beta, so yung sa chi-square distribution, yung alpha is equal to p over 2. Tapos yung scale parameter beta is equal to 2. So, so chapter 3, we consider sampling from a normal distribution. Then we were able to determine the properties of this sample mean and the sample variance. The first one, x bar, and then or the sample mean and the sample variance are independent. We also have the distribution of our sample mean having a normal distribution with mean mu, the same with the mean of our population, but the variance is sigma square over n. And then after that, we have this property that the expression in which the numerator is the product of n minus 1 times the sample variance s sub, s sub n square divided by the population variance will have a chi-square distribution with n minus 1 degrees of freedom. And then we also learned that the chi-square distribution is a special case of a gamma distribution. And then some properties of a chi-square distribution, say if we have a random variable having a standard normal distribution. If we're going to square this, then we have a random variable having a chi-square distribution with 1 degree of freedom. And then if we have mutually independent random variables having a chi-square distribution with p sub I degrees of freedom, no? For x sub I having a p sub I degrees of freedom, then the sum, no, the sum of these random variables having a chi-square distribution, they are not identically distributed because they have different degrees of freedom, but they are parang kung sila, no? We have a chi-square distribution. Then the sum of these random variables will also have a chi-square distribution, but its degrees of freedom is the sum of the corresponding, no, degrees of freedom of these independent random variables. And then, ano pa yun? Sa review. Okay, so we're done. And then we derive also the distribution of, we derive the t distribution, and then the f distribution can be derived similarly uh, uh, in the same process of deriving the t distribution. So we have also some properties of our f distribution stated in theorem 5.3.18. Yan yung sa section 3. So, dalawa na lang sections ang naiiwan, yung order statistics, and then last will be the convergence concepts. This is for the last two sections of chapter 5 that will be included, no, in probability theory, the subject probability theory. Any questions or clarifications? Okay, so let us proceed to section 4 of chapter 5. We have the order statistics. Okay. Sample values such as the smallest, the largest, the middle observation from a random sample can provide additional summary information. We have a particular example here. The highest flood waters or the lowest winter temperature recorded during the last 50 years might be useful data when planning for future emergencies. So these observations provide an additional information for us. We have also the median price of houses sold during the previous month might be useful for estimating the cost of living. So these are examples of order statistics. So the formal definition, we have a random sample, x sub 1 up to x sub m. If we're going to place this in ascending order, we denote it by this notations. The x sub 1, the x sub quantity 1 up to x sub quantity n. And we call this as the order statistics. So that satisfies that the x sub quantity 1, or tawagin na lang natin itong the first order statistic, and this one is the nth order statistic. So the first order statistic is less than or equal to the second order statistic, and so on and so forth, and this is less than or equal to the nth order statistic. So mathematically, we can define x sub 1 here, x sub quantity 1 as the minimum of all random variables x sub I from 1 up to n. X sub quantity 2, it's the second smallest random variable, x sub I from 1 up to n pa rin. And then the x sub quantity n, or the nth order statistic, that's the maximum of the random variables x sub I from 1 up to n, inclusive. Okay, so these are order statistics. So we can now compute, we can now, we can compute probabilities on the on some values of these random variables. So to be able to compute the probabilities, we need the PDF as well as or the PMF of these order statistics. Okay, so before determining these distribution functions, consider first some definitions. We have the sample range denoted by R. It's actually the difference, no? This difference, the nth order statistic minus the first order statistic. It's the distance between the smallest and largest observations. So it's a measure of dispersion in the sample and should reflect the dispersion in the population. And then we have another random variable here. We have the sample median denoted by capital letter M. So M here is equal to this order statistic X sub quantity n plus 1 over 2 if our n here is odd, small n. And then M is equal to the average, no, of the order statistic X sub n over 2 plus X sub n over 2 plus 1 if we have n that is even. So the median is a measure of location as an alternative of our sample mean. So one advantage of the sample median is that it is less affected by extreme observations, since we are just considering the two random variables, mostly in the middle of our ordered observations. Okay, so for any number p between 0 and 1, the 100th sample percentile is the observation such that approximately the product NP of the observations are less than this observation. And then n times 1 minus p of the observations are greater than this 100th sample percentile observation. Definition 5.4.2, the notation. We have this B enclosed by a set braces. If this is appearing in a subscript, it is defined to be the number rounded to the nearest integer in the usual rounding off number. Okay, so the 100th percentile is this order statistic. Okay, take note, no? Naka-indicate na ngayon dito. We have the meron siyang set braces, no, NP, appearing as a subscript in our random variable. Parang ganito yung pagka-express niyan. X, then we have NP. This would be equal to, sorry. Ito pala yan, the 100 percentile. It is equal to that. Okay, so if 1 over 2n is less than p, and then this p is less than 0.5. It is x. Then we have here n plus 1 minus n times 1 minus p if, okay, so we have p here is greater than 0.5, that is less than 1 minus 1 over 2n. Okay, say for example, no, consider natin yung example natin nasa itaas. When n is equal to 12, so if we're going to find, no, the 65th percentile, what is the 65th percentile? So in this case, our p-value here is 0.65. So if p-value is 0.65, we're going to use the second expression. Itong nasa ibaba. because P is greater than 0.5. Okay, now, yung nasa subscript ng ating random variable, we have here n plus 1 minus, we have here n times 1 minus P. So that's equal to 12 plus 1 minus. So ang n natin is 12. 1 minus 0.65, that's actually 0.35. So we have here 12 plus 1 minus, we have here 4.2. So it's been enclosed by our set braces, 4.2. And according to our definition, it's the integer value in which it's being rounded to the usual way, rounding of number. So we have here 12 plus 1 minus 4. Okay, if we're going to round 4.2 as an integer in the usual way, so that is equal to 4. And this is equal to 9. Therefore, the 65th, no, the 65th the 65th percentile is this order statistic x sub quantity 9. Not a random sample x sub 1, x sub 2 up to x sub 12 because n is equal to 12. So what we're going to determine what is the 65th percentile. So the 65th percentile is the order statistic x sub quantity 9. We have here cases when p is equal to 0.5, less than 0.5 and p greater than 0.5. They are defined separately because we have here a piecewise function. Ito yun, meron tayong piecewise function dito. So we have a piecewise function. This is being defined separately, no? We have a piecewise function. When p is less than 0.5, then when p is greater than 0.5. Okay, so it's defined separately so that the sample percentiles exhibit the following symmetry. So if the 100th sample percentile is the ith smallest observation, then the 100th times 1 minus p pth sample percentile should be the ith largest observation because of symmetry. Okay, we have here an example that if n is equal to 11, then the 30th sample percentile, we have here the order statistic x sub quantity 3. And the 70th sample percentile is the this order statistic x sub quantity 9. Okay, so that's for the first part of the order statistic. Kung pato no, definition pa lang, mga definition of the order statistic. We have the range, we have the sample median, we have the first order statistic, we have also the maximum order statistic, or the smallest order statistic x sub 1, the maximum order statistic, we have x sub quantity n. Okay, so let us now proceed to determine the PDF or the PMF of our order statistics. Five point four. Okay, so we have here in theorem 5.4.3. This is for the discrete case. No? Let x sub 1 up to x sub n be a random sample from a discrete distribution with PMF. Okay, this is the PMF. F sub x of evaluated at x sub I will be equal to p sub I, where x sub 1, this realized value x sub 1 is less than x sub 2, and so on and so forth, are the possible values of x in ascending order. Okay, since we have a random sample here. And then we define capital P sub 0 to be equal to 0, P sub 1 to be small p sub 1, then P sub 2, capital P sub 2 to be the sum P sub 1 plus P sub 2, and so on and so forth. The P sub I will be equal to the sum of these small probabilities, no? P sub 1, P sub 2, up to P sub I. Okay, having a random sample, x sub 1 up to x sub n, then we denote this order statistics, x sub quantity 1, and so on and so forth, to x sub quantity n, based on our sample. Then if we're going to determine the probability that the order statistic, the jth order statistic, is less than or equal to x sub I, somehow this is the parang the cumulative, no, distribution function for the discrete case. Then we have here the finite summation of n taken k at a time, the capital P sub a to the k, 1 minus P sub I raised to n minus k, k equals j up to n. And then for the specific value of our order statistic, x sub j, determining its probability, we'll have this summation. Okay? Hindi ko na lang basahin niya. That we're going to use that equation 5.4.3. If you want to know the proof of this, you can see the proof in the book of Casella and Berger. This is for the discrete case. Okay, let's proceed to the continuous case. Okay, we have a random sample x sub 1 up to x sub m n from a continuous population, and then since we know the probability is 0 for any two random variables having to be equal, then thus the probability that x sub the order statistic x sub 1, the order statistic x sub quantity 1 is less than the order statistic x sub quantity 2, and so on and so forth, less than the order statistic of x sub n, that would be equal to 1. Okay, that's the property of a cumulative distribution function. Okay, and the sample space for our random vector, we have a random vector of order statistics. We have here the set of all n tuples, x sub 1 up to x sub n, such that x sub 1 is less than x sub 2, and so on and so forth, but it is less than x sub n. So that's the sample space of our random vector of order statistics. Okay, so we're going to define now the probability density function for our order statistic, and then after that, finding the probability distribution function, or the PDF, if we have for the joint of two order statistics. So dalawa lang muna. So let x sub quantity 1 up to x sub quantity n denote the order statistics from our random sample. With a population, continuous population with CDF, big F sub x of x, and then the PDF, small f sub x of x. Then, if we're going to determine the PDF of this order statistic, x sub j of x, we have this formula. So we have n factorial over j minus 1 factorial times the n minus j factorial. And then we have here the PDF times the CDF raised to j minus 1 times 1 minus the CDF raised to n minus j. So to illustrate this theorem, let's consider a random sample coming from a uniform distribution. So uniform 0, 1, this is actually a standard distribution. does not depend on any parameter. We have only 0 and 1 here, the interval 0 to 1. So the density, the PDF for that will be equal to 1. And then for x in the interval 0 to 1. And then the CDF of that random variable would be equal to x for x element in the open interval 0 to 1. So if we're going to determine the PDF of the order statistic x subquantity j using theorem using the theorem above 5.4.4, okay, so n. So n tayo arbitrary n number of random variables. So n factorial over j minus 1 factorial n minus j factorial. And then our PDF. Ano yung PDF natin dito? 1. So dapat meron pang 1 dyan. 1 times. So ito yung CDF x. Kasi yung CDF x raised to j minus 1 using that formula. Raising j minus 1. 1 minus the CDF, which is x, raised to n minus j. Ito, n minus j. X on the interval 0 to 1. Exclusive. Okay, so using, again, the gamma function, kung meron tayong gamma of t plus 1, that would be equal to t factorial. T factorial na yan siya. So, ibig sabihin, yung n factorial can be expressed as gamma of n plus 1. Tapos, yung j minus 1 factorial dyan, ito, j minus 1 factorial can be expressed as gamma of j. And then, yung n minus j factorial, yung n minus j factorial, it could be expressed as, okay, n minus j factorial. So that would be the gamma of n minus j plus 1. Ito lang ginagamit natin na concept, the gamma function. And then, yung n minus j dito can be expressed as that. N minus j plus 1 minus 1. Okay, notice now, this is actually equal to, itong part na to. This is actually equal to 1 minus beta. 1 minus beta, so using the beta, yung alpha natin dyan would be equal to j, okay? And then yung beta would be equal to n minus j plus 1. Because if we have here beta, alpha, beta, that's actually equal to gamma of alpha, gamma of beta over gamma of alpha plus beta. Okay, so notice now, notice that the jth order statistic coming from a uniform 0-1 distribution or random sample will have a beta j n minus j plus 1 distribution. Ano nga yung natin? Ano nga yung ating, you have learned this in chapter 3. Kung meron tayong beta, so kung meron tayong random variable na x, na meron siyang beta distribution, beta, alpha, beta, yung kanyang PDF, ganito yung form. 1 minus b of alpha, beta, and then we have here x raised to alpha minus 1. Then we have 1 minus x raised to beta minus 1. and then the support for this. So in this case, alpha beta man tayo. Yep. Pwede pa rin yan. Okay, we have that. So kung makikita nyo dito, based on this, so we have now 1 minus beta. Itong part na to. You have this. So J is the alpha. Itong J dito. That's the alpha. Yung beta natin, n minus J. Okay, so we're able to derive now the distribution of our order statistic X sub quantity G, in which we have a random sample coming from a uniform 0, 1 distribution. So since we already have our PDF for this order statistic X sub quantity J, then we can determine the moments. Ito muna, the mean or the variance. These are because the variance is a special case of moments. Expectation of the X sub J, X sub quantity J. The mean for that, having a beta distribution, we have alpha over alpha plus beta. So in this case, your alpha is J over alpha plus beta. Parang ganun yun. We have here alpha, we have J, alpha plus beta, J plus n minus J plus 1. Okay, so we have these results. And then we have the variance. Kung dito tayo, no? The mean of X here, we have alpha over alpha plus beta. Kung yung variance naman ng X, we have this formula, alpha beta over alpha plus beta quantity square times alpha plus beta plus 1. Okay, yan yung gagamitin nyo. In which this is your alpha. Itong part na to, this is your beta. So we have that variance of our order statistic X sub quantity J. Okay, so this is an example illustrating our theorem 5.4.4. In a case that we have only one order statistic. Okay, so hanggang 11 lang tayo, no? Yeah, 9:30 to 11. So, lumampas na tayo. So I'm going to continue this this afternoon. Okay lang ba kayo mamayang hapon?
Sir.
Okay, so any questions or clarifications before we go? So nagsimula akong mag-discuss na ngayon ng order statistics. So yung first part, we have those definitions of order statistic. We have the finding the cumulative distribution function for a discrete case. We have a discrete random variable, random sample. And then after that, we have the continuous, if we have a continuous random sample, determining the probability density function of an order statistic. And this afternoon, I'm going to continue, say, finding the PDF of the vector in which we have a vector of order statistics. Or we can also determine the marginal probability density function for these order statistics. Any questions or clarifications? None so far? Okay, so thank you for giving your time for this makeup class. I'm going to send the link later for our afternoon class. That's all for this afternoon, and class dismiss. I'm going to stop now the recording. Bye.